your supervisor was Stephen Mahing, right?
Yeah, yeah.
And you probably were his last PhD student, or?
I was, yeah, yeah. So, yeah, yeah. So he got sick that winter, and then I graduated, and I already had the job at Oregon. So, but
okay.
yeah, yeah. How did you know him pretty well?
Not well, not well. I met him a few times, but I did go to Berkeley sometime, a good number of years ago, and he was delivering these seminars on open fresco. And, you know,
Oh yeah, yeah. Well,
did you use hybrid simulation in your PhD?
It's funny because I didn't while I was Berkeley, and now I almost exclusively do research in hybrid simulation. So it's like it's funny how things change. Yeah, I'm working a little bit with Andreas Schellenberg, who was involved in like the open fresco, and is still involved. So, but I didn't do any of it for my PhD.
Yeah, yeah. No, I met him there, and it must have been great to do the PhD with him, right?
Oh, he was
but
the best.
Very challenging at the end, I guess. You know.
Yeah, yeah. I mean, I had mostly finished everything. It was just writing. So, but yeah, he was fun. You'd walk into his office, he'd have about 1,000 ideas that you would choose one because there's no way you could do all of them. And then, you'd walk into his office like the next time, and he'd have 1,000 other different ideas that had nothing to do with the first idea, and he'd forgotten already that he gave you the other ideas. So yeah, but it was a blast.
And he was also, well, I don't know, at least in that seminar that I attended, he was quite funny, like a nice person to be around. He was very kind, and it instilled trustworthiness.
Yeah. No, he was.
Well, a very big name as well. A bit daunting in that sense.
Yeah, well, I forgot about that part with time. But yes, like I think the first time I met him, I was a little bit intimidated. But I did a kind of longer PhD, so by like year 5, it was fine. I kind of forgotten that part.
Okay, so I will present you. I mean, for those of you in the audience that don't know Barbara, if you could, I probably should say that if you could remain muted over the presentation, that would be great. And then we will have questions at the end. So Barbara is assistant professor at Oregon State University, and she graduated from UC Berkeley with a PhD. And your degree was in Kansas, I guess, right? Civil engineering, your first degree, and then you did a PhD and an MSc in Berkeley. And Barbara works on innovative structural systems. She has some great work on brace frames and spine, these stiff spine sort of systems, and she's now working a lot on real-time hybrid simulation, and this time involving some fluid structure interaction, which is quite challenging, I would expect. So, all to you, Barbara, please.
Okay, so let me just share my screen again. So everybody is good and can see this?
Yes, yes, I can see.
Great. So I'm actually going to be presenting some of the work from a student who just graduated and completed our first round of really pilot hybrid simulation tests at Oregon State this past January. And then we have a couple more rounds of more complex testing that are coming up in the next year. Is it clicking? There we go. But just to give you a general outline of what I'm going to be talking about. So I'm going to give you some motivation for why we're maybe going to want to apply a hybrid approach to this problem of studying fluid structure interaction. And then I'll go into sort of this method of what is this real-time hybrid simulation approach, specifically applied to a fluid structure interaction problem. And I'll go more into this pilot study that the student has just wrapped up that really has a civil engineering emphasis, where we're looking at cascading, seismic, and tsunami hazards, and then go into some further extensions of some of these more complex problems that really become quite interesting. So after we got this pilot study up and running, we can start really looking at more complex and more interesting problems. But really, here's the motivation, and I'm going to put this in a civil engineering context and mostly towards civil structures, but there's a number of other structures that this could also be applied to. So here we have the damage after the 2011 Tohoku and earthquake and tsunami in Japan. And many of these bridges survived the earthquake, but then failed under the subsequent hydrodynamic loads induced by the tsunami. And so in Oregon, we have very similar coastal hazards, particularly we're talking about the seismic and then the tsunami waves following it. But really studying this is constrained by a couple different things. First off, when we get and want to study this in an experimental setting, we're often having to scale down our structure to pretty small scale. And that's just because of the size and capacity of our existing hydrodynamic facilities. On the opposite side of that, when we start looking at fluid structure interaction problems where the structure is actually interacting and reacting to what's happening to the fluid and vice versa, it's incredibly costly. And by costly, I mean running computations and the fluid structure interaction side can take a lot of time. And we're talking about, depending on the size of the problems, hours to days to weeks. And so what I call this is the simulation paradox. So you have this fluid structure interaction problem that's constrained really by the small scale that you have in the wave facility. And so I just have some example here of some experiments that we have in our wave flume at Oregon State and wave basin. So we can test structural elements or structural components due to the size. We can look at the building scale, but now we're looking at a smaller scale, in this case 1:6. And when we start looking at the community scale, we're really looking at something that's pretty highly idealized when it comes to the structural systems. And so this kind of leads to this paradox, is that you need these physical models to really validate the computational models. So these numerical models of fluid structure interaction are pretty complex and subject to pretty large modeling uncertainty. So you need experimental data to really validate them. But then you have these physical models that are scaled down at small scale. And because of that, they really might not represent full-scale structural response. And so I call this the simulation paradox. And so when we start looking at this small-scale problem and we start looking at structures subjected to multiple physics, then this really becomes more and more of an issue. So here I have a house, maybe subjected to some sort of hurricane loading. So you have the waves impacting the structure, and then you also have wind impacting the structure, and then you have the structure's dynamics. So when we scale down structural specimens for experiments, we want to satisfy the geometry. So we scale down the length based on whatever our original full-scale structural model was. We also want to satisfy some sort of kinematic similitude, so similar velocity and flow. But the one that I think is quite interesting is the dynamic similitude, and that's that you want similar forces in your small scale model as you have in your experiment. And the issue with that is that each one of these parts of the multi-physics problem all correspond to different forces that tend to govern the system. So for example, when we scale down for wind, we're typically looking at Reynolds number, the structure, maybe we're interested in that combination of inertial forces to elastic forces, and then we're looking at the waves, we typically scale by Froude. And so what this means, so if we look at the Reynolds number, and the length scale is on the x-axis and the time scale is on the y-axis. So as you scale down to smaller and smaller scale, your time scale shrinks so that you can keep the same ratio of forces in your model scale as you have in your full scale. And so you have Reynolds scaling here. If you want to scale the waves part of the problem, you have Froude scaling here. And if you want to scale the structure, you might have this scaling here. But when you look at all of these different types of similitude, the only time that they're equivalent is when you have a structure that's at full scale. And so what typically occurs is you scale with respect to one of these forces in your experiment, and then you either neglect or simplify the other forces that might be happening in the experiment. And so perfect dynamic similitude between all the forces that might be relevant to your problem is really impossible in these traditional hydrodynamic experiments. And so partial similitude, where you select one and maybe modify or skew the others, is accepted. And so you have a system that might not represent full-scale structural response. And so at Oregon State, we've been working on sort of a way to mitigate this scaling issue, and we're calling it real-time hybrid simulation. And we're implementing it specifically for fluid structure interaction. And what hybrid simulation does is it kind of combines the best of both worlds. So I mentioned that simulation paradox where we have a computational model and a physical model. So we're going to sort of take both of those and try to take the advantages from both and have them talk and interact with each other. And so we can take a system like what you see here and split it up into a physical side and a numerical side. So at Oregon State, we're focusing on modeling the wave structure interaction physically. So that's this red component of this diagram. And then the remaining structure we can model numerically, which is the blue part of this diagram. And so we can imagine if our physical model is in our flume and is at small scale, then whatever measurements that we extract from the small scale model, we can scale that up by Froude and send it to the full scale numerical portion of the system. And then that can interact with the other portion of the system by scaling it down by Froude. And so the numerical part of our system can be at full scale, and it can interact with the small scale portion of whatever forces are of interest to us. In this case, the waves and the potential wave structure interaction. And the nice thing about splitting up the system in this way is now we have the physical part of our system that allows for really fast testing of the wave. So now we're not dealing with a computational model for fluid structure interaction. We have a wave that runs in real time. It's a real wave, and we're not waiting days to weeks to do any sort of computational fluid dynamics. We also have flow that's real. So because the wave structure interaction is real and it's physical, we have reduced uncertainties associated with that part of the problem. And now if we connect it to the remaining numerical portion, now we can really go a bit crazy. And so you can have the numerical portion be at full scale. It can be pretty complex in interacting with the physical portion. And then we can also switch out and mix and match that numerical portion to whatever we're doing on the physical side. And so you can imagine that you can test a lot more range of structural response as you flip out this numerical portion of the system. And so this isn't a new idea. Sort of this offline type of testing has been conducted in the past. And so here is our wave flume at Oregon State in a 1:5 scale bridge stack. And so what they did here is to sort of emulate the elastic forces and sort of structural response. They put these springs at these bed caps on the bridge. And then what they did is they measured those forces, scaled that up, and then tested it at full scale as sort of a component test. And so this was sort of an offline way of looking at this problem. And so here on the left, you can see sort of the rigid bridge where they don't have that spring emulating those elastic properties. And then on the right, you're seeing how much that the forces in the system can really change once you consider the structural dynamics. And so that was sort of a step in this direction of maybe using a two-step type of approach, but addressing the similitude concerns that you might have with these small-scale experiments. And so if a traditional approach, you might say that the bridge is modeled pretty rigidly, or that the structural dynamics are totally neglected, and you're looking at the wave side of the problem. So you're just looking at how the fluid sort of flows around whatever this specimen looks like. So that second phase, you can imagine also looking at some structural dynamics by replacing or having part of the system have a spring, like a mechanical spring. But then what if you wanted more more control over that spring, so you could replace that spring for this bridge deck with an actuator. And then the part that we've been calling hydrodynamic real-time hybrid simulation actually says, well, what if you actually use that actuator to emulate the remaining portion of the bridge? And so the remaining portion of that bridge is all numerically simulated and then interacting with the experiment. And so now you can imagine using this hybrid simulation where you combine a numerical model with a physical model, you can really extend the sophistication of what you're able to test in these flumes. And of course, you can play around with scales and have the numerical side be full scale and the physical side be small scale. And so this sort of kicked off a pilot program at Oregon State. And so what we've been doing is sort of studying this bridge sphere that's part of a larger bridge model. And so you can imagine that this bridge model can be at full scale. We can then take the displacements coming out of our hybrid simulation. We can scale those down by Froude, apply them in the physical tests, and then measure the forces, scale those up by Froude, and feed those back in to sort of talk to the numerical model. And so I'm just going to play this video here. And I hope this is coming through over the Wi-Fi. But what you should be seeing is that the wave is slowed down. And the issue here, as much as I would like the behavior of this wave structure interaction to be this way, so to the point where I can slow down the wave, the reality is I can't. So we're using real water. And so we have to keep up with the fluid flow. Which means that this interaction between the numerical model and the physical model, if you're doing it simultaneously, has to occur in real time. And the issue with that is that as you go to smaller scale models, you actually have to have this interaction occur in faster in real time, because as you scale the model down, your time also scales to keep up with the dynamic similitude. So it's a pretty hard problem, and it requires pretty fast computational models on the numerical side, as well as whatever communication you have between the physical and numerical component. And so to start out, we took this hard problem and we really simplified it. And we sort of applied these traditional hybrid simulation approaches that were developed in really the seismic world and earthquake engineering. And we started just baby steps applying it to this fluid structure interaction problem. So hybrid simulation, or it used to be called online testing, is something that has been around for quite some time. So one of the first papers came out in 1975, and it started out in the earthquake engineering community. And it hasn't really been until recently that we've been capable of doing this sort of real-time hybrid simulation. And that's just because of the evolution of computer architectures, and now we're just able to do computations that much faster. And so what hybrid simulation does, like I said before, it divides your system up into a numerical component, which is housed on some sort of computer, and a physical component, which might be in the lab. And I'm going to sort of set this up in sort of a traditional approach based on the earthquake engineering problem. And so these two systems, or these two sub-assemblies, are coupled together through the equations of motion. And that typically is solved through some sort of finite element analysis, where you integrate the equation of motion through time, and then you solve for the displacements the next time step. And once you have those displacements, and it's an earthquake problem, and so usually what happens is that seismic input is simulated on the numerical side, but it could also be, say, in a shake table specimen, simulated on the physical side. So you have your problem, and so you integrate it in time and solve for the next time step, and then you numerically send displacements to the numerical portion, and then you physically actuate the displacements in the physical portion of your system. And then based on those displacements, you either do some sort of state determination and determine your restoring forces in your numerical model, and then you also have some sort of sensor measurements and a data acquisition on the physical side, where you measure the forces in your physical model. You feed that back into the equation of motion, and then you solve for the next time step using whatever integration scheme that you happen to choose. So by doing this, you get more realistic structural response, because now any portion that maybe you're uncertain of, you can model physically, and then you can have more realistic boundary conditions and more complex models by modeling the remaining of this portion of the structure numerically. So what we're doing in this hydrodynamic-RTHS approach, or hydro-RTHS approach, is instead of having that earthquake load being applied externally or being applied numerically, what we have is a physical wave. And so we kind of break the problem down in a little bit more detail. So instead of having the earthquake, where we then measure the restoring forces in the system, what we can do instead is we can have a wave impacting our structure, and that can sort of feed into the right-hand side of this equation. And so we can take that wave force and apply it almost as applied loading to our structure. The nice way of partitioning the system like this is that we're really only solving for the structural dynamics. And so in no way do we have to come up with new equations that also include the fluid side of the problem. And so we can sort of capture this problem in a very traditional approach where we're focusing on the structure rather than on the fluid. And so it's kind of an indirect way of including what the wave is doing to the structural response. And so this is sort of replacing that RP that I had on the previous slide with this new applied force that's applied on the right-hand side of the equation. And this is what we're calling hydro-RTHS. And so this is what we did in this very basic, very preliminary pilot study where we sought to see whether this testing approach was even feasible. And so we have some pretty large-scale facilities at Oregon State University. So in this case, we're using our large wave flume. And we took this problem and sort of thought, well, you know, we have this numerical portion where we can study the bridge, and then we have this physical portion where we could maybe look at a pier, and this happened to be an existing specimen. And so, well, since we're already sort of mixing and matching and playing around with this hybrid simulation approach, why don't we also apply an earthquake motion in an offline manner? So we're actually looking at cascading earthquakes and followed by tsunami events. And so what we could do is we can apply an earthquake numerically to the bridge, monitor the damage, sort of set that damage in the physical system, apply any residual displacements that we wanted, and then physically apply the wave in the wave flume. And so in this way, this entire system also incorporates potential previous damage from the previous earthquake loading. And so the specimen looked like this. So we had an existing specimen that we were leveraging for this project. I'm not saying that this is one that is necessarily of interest to the civil engineering community. I mean, it's a cylinder, the flow wants to go around it quite nicely. But for the sake of this problem, it was an existing specimen, and it allowed us to look at relatively simple response. So the existing specimen had a pin and a load cell at the base, and then it was placed along our flume, and then there was an actuator at the top of the cylinder, which we use to monitor displacements, as well as measure the forces that were delivered back into the equations of motion. And then on the numerical side, we had a relatively simple bridge model that was a 3-span bridge. We gave it, even though this orange cylinder specimen that we had was hollow and made of steel, because we're hooking it up to this numerical model, we can actually give it more realistic bridge properties. And so we gave the concrete piers sort of realistic stiffness properties of a concrete section. We also included some soil structure interaction at the base of these piers, and so we can sort of see how that might affect the bridge response. And then you have the wave that we had impacting one of the bridge piers, which in this case, I know I emphasized that you really want to use this hybrid simulation approach because of its similitude advantages. We decided to go at full scale just because it was the first time we'd ever really done this testing approach. And so the numerical model was scaled to the physical model, and then the remainder of the bridge was actually scaled to an existing bridge model that we had to give it more realistic stiffness and geometric properties. And so we called this the dummy bridge model. It's not something that we're not necessarily looking at to look at accurate bridge response. It was more to set up and test the hybrid simulation part of the system. Now, I don't know if you noticed, but we have this soil structure interaction spring at the base of the numerical model, which doesn't exist in the physical model. So in the numerical model, we sort of have this 2 degrees of freedom that are constrained in translation, and then a rotational spring in between to sort of look at some soil structure interaction effects. And then in the physical model, we have this pin at the base. And so to sort of mitigate some of these equilibrium issues, what we ended up doing is in the numerical side, we put in a very stiff element wherever we were representing our physical pier, which really is intended to act like a rigid link. And because of that, to satisfy equilibrium between the numerical model and the physical model, even though they have different boundary conditions, by using this rigid link, you've now constrained the rotational degree of freedom at the base to whatever translation you're applying at the top. And so now you don't really have to have that as a degree of freedom, an extra degree of freedom in your system. And then also the translations between these 2 nodes sort of sandwiching that spring, they're both fixed in translation, and so they're not part of your degrees of freedom as well. And so when you set up the equations of motion, those degrees of freedom aren't really there. And so in that way, equilibrium is sort of satisfied between these numerical and physical models. And it's not exactly something that I would recommend for every testing case, but again, this is a pilot study, and we were just playing around with what we could do with this numerical model, relatively simple 3-span model, and this physical cylindrical specimen. And then we started looking at this cascading seismic and tsunami events. And so we looked at a couple different cases to kind of gauge when the hybrid simulation was really coming into play. So we did a cold place where we had the hydraulics turned on the actuator, and we just sort of held the cylinder in place and then impacted it with some sort of wave loading. We also looked at some sort of sine loading condition. So we displaced the specimen back and forth and then impacted the specimen with the wave while it was being moved back and forth under some sort of sine loading with some sort of frequency. And in that way, we have the motion of the body also interacting with the system, and we could look at how that might change our forces, and then look at sort of what's happening on the wave side when you have a wave impacting a moving body, and in this case, maybe using the Morrison equation as a simplified way of looking at it. And then you have the Hydrodynamic-RTHS, where we have a physical wave impacting a portion of the model, which is interacting with the remainder of the bridge. And then we measure the force at that top load cell and feed it back into our equations of motion. And then to see if we could get something more realistic, because a tsunami would most likely impact both bridge piers, we could actually copy that physical wave loading and apply it to multiple bridge piers, assuming that they received the same wave loading. We can apply sort of an offline seismic loading in order to get some previous damaged states. And then again, because we were playing around and we could really do whatever we wanted on the numerical side, we could also look at scaling those hydrodynamic forces up a little bit. So in our wave flume, we're not allowed to use anything but clear water. But as a tsunami rolls in, it actually picks up quite a bit of debris, and the density of that water can change quite dramatically. And so to sort of account for the influence of that higher density on the bridge model, we could actually say scale up those forces by a factor of 1.5-ish. That's sort of the ratio between maybe the higher density tsunami wave compared to the clear water physical waves that we had in our facility. So there's a lot of different things that we can do here. And then here's just one of the tests for the hold case. So you can see at the other end, and this isn't a very formal image, I have to say, shot on the iPhone. But at the end of this, you have the wave machine, and you can see the wave coming in and then impacting the pier. And in this case, we're holding it in place. But in the case where we have the real-time hybrid simulation, it would actually react to that loading. So in the hold case, as you can see here, we have, there's no displacements, and then we're kind of holding it at the top, and you can see the force at that top load cell, and then also the force of the bottom load cell. And then when we look at this, we did several different runs of the hybrid simulation, but if we look at the hybrid simulation, we see something that's a little bit different. So what I'm just showing here is just due to the wave loading. So we've already applied the seismic loading offline. And so these bridge piers, you have some residual displacements from the previous seismic loading and previous bridge damage. And then the bridge is really responding to sort of a short pulse And so the wave is acting like a short pulse that you might see in a structural dynamics problem, and then you're seeing the resulting oscillations of the bridge. As a result of that, you're seeing this 1.5 times factor coming to play in the forces. It's difficult to see. So in the case of the period we chose for this bridge specimen, the peaks aren't really so much being affected, but after the wave applies and this structure is sort of oscillating, you do affect the wave loading after that peak. And you can actually affect the peak as well as you sort of play around with this, the period of this bridge specimen with respect to whatever the duration of your wave loading is. And so we can see that at the force of the top load cell. And then when we start looking at equilibrium between what we're seeing, say, on the numerical side, where we have that SSI spring and the boundary conditions are different compared to what we have from the data acquisition system, where we have, the cylinder that's pinned at the base, we can see that we are still satisfying equilibrium because we're using that rigid link and because we have those fixed constraints at the base of this pier. And here's just some plots. We had relatively minimal error, and it was just a pretty good round of preliminary testing. And we're just going to go to more and more complex things testing as we go forward. And so some of the next steps is sort of playing around with the numerical side of this problem and trying to do something that's more complex on the numerical side. Remember, we have to be in real time or faster than real time to satisfy dynamic similitude. And so we can add more degrees of freedom, more mechanisms of inelastic response on the numerical side. We can also look at similitude. So in the case of the previous bridge that I just showed you, this very introductory dummy bridge, we said everything was at full scale, and so we scaled to the size of the cylinder. But we could also look at this in terms of these, in terms of scaling up or scaling down by Froude in order to represent the numerical side at full scale. We intentionally had the dummy bridge model remain elastic under the wave loading. So we were just looking at elastic bridge response, but we can also have the system maybe have some inelastic behavior under the wave loading. And by the time we add all of these things in, and we're running faster than real time because of the Froude scaling, and we're looking at inelastic response, and we have more degrees of freedom, what we really need is parallel processing. And so some of the preliminary studies that we did for this more complex bridge arrangement, we're really running the numerical side of the problem in parallel on multiple CPUs, in this case, 8 CPU cores. And then on the physical side, the cylinder, like I said, isn't really something that is very interesting to look at in terms of the wave structure interaction, but having increased area of impact or more complex physical models, say as in this bridge deck, you can really start looking at very, very interesting problems. And one of those interesting problems is something that we've been kind of looking at for about 1.5 years now, and it has to do with this multi-physics part. So I mentioned before, you might have wind in your system, which tends to be scaled by Reynolds, and then you have the waves in your system, which tends to be scaled by Froude, and then you also have the structural dynamics that are part of your system. And satisfying all three of these is very, very complicated. And so in many problems where you have multiple fluids, say in floating offshore wind, what you can do is you have a specimen, a wind turbine specimen that's floating in, say, these very large wave basin facilities. And then what some of these laboratories have done is that they've physically applied wind. Now, the issue with this is that the scaling of your wind is incorrect because you can't scale the wind along with the waves, and often the structural dynamics is neglected, but if you wanted to include that as well, all at once, it's relatively impossible. And so having these sort of two fluid systems is really hard to test in existing laboratory facilities. And so what we've been doing at Oregon State is we said, well, what if we could take that portion of the problem, that wind portion of the problem, and just have it at full scale in a numerical model? And just like the previous slides, it's sort of interacting with what's ever happening on the physical side, and then scaled up or down by whatever similitude requirement you want to add. And this isn't a new idea. They've been studying this quite extensively in Norway, and I just have a figure on the right where they've been using cables to sort of actuate the wind loading onto this specimen, and then the wave loading and the small scale turbine are all physical. So we're kind of taking a little bit of a different approach. And so we have a numerical side that represents our aerodynamics, our servodynamics, and potentially also our structural dynamics, that is then communicating with a wind turbine in our basin, which then we're actuating on with a robotic arm. And so this is kind of a fun project that's more of an extension of that previous pilot study I showed. And you can really imagine how you can test some pretty complex things once you start adding the numerical portion of the numerical part to this overall system. And so I'm just going to quickly go through some takeaways. And so at Oregon State, we can now virtually extend our flume through hooking it up, whatever's happening on the physical side, with a numerical model. We've also shown that it's relatively feasible, and that we can now start looking at more complex structural systems and more complex wave structure interaction problems. So you have this wave that runs in real time, and so you can look at a lot more models and accumulate more data. And then you can use this potentially more accurate data to validate these computational models and look at it on a computational framework. And then you can also sort of mitigate any challenges you might have with having a small scale model in a flume on the physical side by having your numerical model be at full scale. And so there's a lot of ongoing work sort of extending this, mainly determine which scenarios we need this hydro-RTHS. There's not like, it's yes, you could potentially virtually extend your flume, but it really is a case-by-case basis on whether this is really needed and what your problem is, and whether you need this sort of complex interaction between a numerical model and a physical model for every case. And so figuring out where that line needs to be drawn and when you need hybrid simulation versus when you don't is still needed. We haven't yet turned or toggled on and off these various scaling laws between the numerical and physical portion. And then really the speed is a big one. And that's because, again, as you scale this model down to small scale, you have to be running in faster than real time. And so your numerical model has to keep up with that. You have to be doing computations in faster than real time. And that's incredibly difficult. And so finding the limits of how fast you're able to go, and of course that depends on what your numerical model looks like and the number of degrees of freedom and sort of the level of nonlinearity, this is probably going to constrain the hybrid simulation approach. And then finally, sort of looking at different aspects of that numerical model and looking at greater degrees of nonlinearity during the wave loading is going to be important. And with that, I'll wrap up the presentation. And thank you so much for inviting me. This is quite fun to participate virtually from the US during a seminar. So I'd be happy to answer any questions.
Yeah, no, thank you very much, Barbara. Fantastic work that you're doing there. It's quite amazing and inspiring, actually. I would invite the audience, if they have any questions, just raise your hand or directly unmute yourself and ask the question. While they warm up, it seems to me that from what you are saying, the bottleneck at the moment is in computation in all these.
Yes.
So all these feedbacks that you have is not really a problem at the moment. It's more the numerical.
Right now, it's not a problem. But that potentially could be a problem too, because so we're using ScramNet right now, which is sort of everything's hooked up by fiber optic cables and it's a shared memory network. And so the communication is relatively fast. But the issue is you still have, like, you have this much time, and then a portion of that is communication. And so that means, you know, it's not even faster than real time. You still have to, like, have a computational model that's even to go a little bit faster than what's actually needed, because you still need some of that for communication. So that part of the problem's there. But, you know, you still have to fit the numerical model within, you know, whatever deterministic rate if you're doing hard real-time testing, or determine whether you can get away with, say, a soft real-time testing approach. So do you need to, like, have a displacement command like at the frequency of your controller and keep up with it pretty pristinely, or can you have a soft real time and not really lose that much accuracy, where maybe you're not keeping up quite with your physical model? So that's one of the questions that's still out there. So we're not, the communication is part of that bottleneck, but we're really seeing it more on the numerical modeling side.
But I would imagine that when you have this physical representation of your, because this is really what you want to have, the physical representation of the fluid structure interaction, right? So that will immediately impose a very hard constraint on the.
Yes.
So it's.
Yes. But when we have the case of the floating offshore turbine on this sort of periodic wave condition, where we have like extreme, like they're pretty long period waves, maybe we can be a little bit off and still like interpolate forward, and maybe not lose that much accuracy. So in the case, like it depends on the case. Like in the case of the tsunami loading, where it's really this like pulse type effect, you really need to be there, like monitoring it and react to it like right at that point. But some of these other problems where it's a lot more oscillatory, and the periods of the system are much different, you might get away with, say, not being there every single moment. And so,
sorry, continue.
Well, so we're using a predictor corrector type approach where, let's say we can't solve the equations of motion within the constraint, the hard real-time constraint. We can interpolate forward as needed and then correct as needed. And, you know, potentially that's totally appropriate depending on your problem.
And does that have to do with the motivation of including the robotic arm? I mean, you can potentially have more issues there, no?
Yeah, the robotic arm might have been a little bit of a mistake. We might have been too enthusiastic about having a robotic arm in our flume. That has been a challenge. So yeah, I think we at the time had thought and were promised that the robotic technology was there, and that we could like quickly apply 6 degrees of freedom. I think it's actually 7 degrees of freedom for the arm. And it was going to be out of the box, no issues. And the reality is there's a lot of issues there. So all of those degrees of freedom are pretty much cross-coupled. And so it's really difficult to move in 1 degree of freedom without affecting the others. And so if we had set it up with more of like a cable type actuation where we had complete control, like what they're doing in Norway, we had complete control over every degree of freedom, it might have actually been a lot easier. And then you have to deal with the fact that you know, we're dealing with water, and so anything we put in our flume has to be waterproof, or outside of the water, which comes with its own set of constraints. And so if you had cables, you can imagine you're not really affecting the wave loading at all. Like it's just a cable that's in the water. And it's, you know, and who cares if it's in the water? So there's things like that that you don't necessarily think of in a traditional hybrid simulation setting that start coming into play when we start looking at the fluid side of the problem as well. So, but we're gonna get the arm to work. It's gonna work. It's just more challenging than originally expected.
Yeah. No, but it's great. I think it opens a lot of doors as well, right? And it's quite revolutionary. I think maybe that last comment that you had, maybe that influenced also the decision to use a pin base with the soil structure interaction modeled. I mean, because you are feedbacking forces, right? The forces that you read from mainly from the load cell at the bottom, right?
Mainly from the load cell at the top. So we're saying that everything is sort of it's dependent on what's ever happening at the top. It's a 1 degree of freedom part that's in the physical model. Yeah.
Okay, so potentially you can have actual soil and you know, model the.
Yeah. But it's very difficult to do in our flume, and then if you talk to director of our wave lab. He's going to be quite.
They don't want to have sediment there.
They don't want soil or sand or any. I mean, we've done it. Like they did some vegetation testing like a year or so ago, where they made sand dunes. But it's yeah. And then the reason we're sort of careful about the actuators is that they don't want hydraulic fluid in the flume, because it messes up like the water and things like that. And so most of our actuation schemes are looking at like electric waterproof actuators that are like stainless steel and totally submersible. But then everything comes with a price tag.
That's still MTS you're using, or?
In the case of what I just showed, that was still MTS and it was still a hydraulic actuator, but we put it in a plastic bag.
Okay.
So we need to figure out a different way of doing that. So that was.
There is a question from Ashraf. He's asking if I have a question about the numerical modeling technique of the structure. The bridge, for example, so far they are modeled using frame line elements only. Am I right?
Yeah.
And because more detailed simulations will require more computational capabilities and increasing real-time gap, I think, right?
Yes, which is why we started out with this really simple model, and really this model has no problem running in real time. It's so fast, and it's like in the blink of an eye. And actually, when we went to the 5-span model, we do still have line elements, but we have fiber sections. We're modeling the abutments. We're modeling all these different potentials for nonlinear response, and that one has to run in parallel. Like there's no way it would be able to satisfy the time step requirement. So.
George, do you want to ask your question?
Yes, sir. Am I audible?
Yes.
Okay. First of all, I want to thank you, ma'am, for the wonderful presentation. So the question that I had is, in the wave structure interaction problem, so how do you match the physical properties, the properties of the physical specimen to the actual concrete section of the bridge, such as you talked about the shape of the section and the scale of the section. So what about the material properties of the section?
Yeah. So in the case where we impacted one bridge pier, so that experimental element is a rigid link. So you really aren't accounting for the sort of stiffness properties of the section in that case. But the other bridge pier would be purely numerical and would account for that effect. So we're doing that to sort of, because we have that weird equilibrium condition at the base, and we're only actuating that top degree of freedom. So from that, in that respect, it's a rigid link, and so we played around with some ideas of how you could still incorporate the stiffness properties, but you have to make some assumptions, which we weren't really willing to do in this first round of tests. So you have this pretty stiff steel cylinder in the flume, and so really it's this motion of that cylinder and how that affects the wave loading. You're kind of assuming that it's like a triangular displaced shape. It's not like it's some sort of curvature effect that's involved, and everything's elastic. So maybe that's an appropriate assumption. So you could leverage that and say, well, this displacement here, maybe in your numerical model, when you get down to say equilibrium at the base, maybe you can have some stiffness characteristics that numerically you're reflecting some sort of curvature of that pier that's not necessarily what's in your physical portion of your model. But then you get into sort of issues, well, are the forces you're reading in your numerical model satisfying equilibrium with your or that you're reading in your physical model satisfying equilibrium with your numerical model? And it becomes, I'm sure you could do it. We just haven't attempted to really figure out all the assumptions that would be needed to sort of match everything up in that case. And so for this initial pilot study, we said, well, let's just have the wave, and it's only really interacting through some sort of motion of that orange cylinder body. And we really don't have any structural dynamics on the physical side. And then on the numerical side, it's going to be the reaction of the remaining portion of the system to that loading condition.
Okay, thank you, ma'am. One more thing, because this section, like the width of the wave that is coming in is limited, and there are boundaries on the other case, does that affect the forces on when compared to the actual case where there is no limitation, rigid links? So does that make a difference in the forces that is coming into the physical specimen?
Yeah, I mean, that's kind of like we're assuming that we're neglecting that portion of the problem. But you're right, like that could have an effect. But we're kind of assuming that it's really the global response of that pier that's really affecting the wave loading. And I would like to add that the specimen we're testing it's a cylinder, and the fluid flow is really quite nice around the cylinder. It's not like so it's some of the things that we're testing here are pretty idealized and maybe not really interesting problems. Like it might be more interesting to have something that's not a cylinder that maybe has some flexibility to it as well, and maybe also has a different area of impact and maybe some elastic structural properties. And so there's a lot of different things that still need to be looked at that we're only doing in a very preliminary idealized way, because it's really the first time that we've ever done it.
Okay, thank you, ma'am. That's all from my side.
Yeah. Piano, piano, si anda lontano, right? Just a little bit by little bit, because
Yes.
you were validating the methodology. It's quite interesting. Thank you very much, Barbara. Thank you very much for a very nice presentation. I'll close this now. If it were in person, we will be clapping now. But thank you. Thanks a lot. Thanks a lot.
Great. Thank you so much for inviting me.